So we are on a quest to find a complete invariant for knots. In other words, we want to find some mathematical object which, when it measures the same thing for two different knots, we're guaranteed for those two knots to be the same. Up until this point, the invariants we've been able to build, such as the crossing number, the bridge number, the unknotting number, the fraction for a rational tangle, none of them have been perfect. Fractions for rational tangles completely classify rational tangles, but not every knot in the world is built on top of a rational tangle. Similarly, the numerical invariants we've found for knots so far are good insofar as if I have two different diagrams of the same knot, then those numerical invariants are going to measure the same. But it's not always the case that if that numerical invariant is the same for two diagrams, it doesn't always mean that I have the same knot. Right? There are several different knots that have crossing number of 6 or bridge number of 2 or something like that. So those numerical invariants aren't powerful enough. So to get to that next level where we can build a mathematical object that is both sensitive and specific to differentiate between different knots, our tool is going to be knot coloring. This is the basic idea that we could begin looking more closely at structure of knots by thinking about coloring the various strands of the knots a different color. If we can get enough information by coloring the strands in a knot diagram different colors, we may be able to encode just enough information that can completely determine that knot. How we do that is a pretty long story, of which this is just going to be the first step. So the plan is that first we're going to talk about what it means to K-color a knot. So K is going to be a number here, like maybe we're going to 2-color or 6-color or 10-color. Basically ways of assigning colors to arcs on a knot diagram. And from the definition of coloring, we want to derive some arithmetic conditions that can tell me when a knot is tricolorable, when I can color a knot using 3 colors. And it's that arithmetic reality to coloration that's going to give us the link from colorings of knot diagrams into arithmetic, and then algebra, and then into the higher algebraic structures that we're really interested in. Once we get that, we also want to use the tricolorability condition for knots. So if we know what it means to 3-color a knot, we want to expand that out a little bit to come up with a scheme by which we can color rational tangles using integers. And then, just to hook us back into what we know about rational tangles, we'll see what colorations, integer colorations of rational tangles, have to do with the one complete invariant that we know so far in the course, the fraction, the tangle number of a rational tangle. There's a really beautiful relationship between the fraction of a rational tangle and colorations of that rational tangle. This is going to be a really super elegant way, by the way, to compute the fraction of a rational tangle. And then finally, we want to know what are the relationships between those integer colorations of tangles and the colorability of knots that are associated with those tangles. So if I have a rational knot, that knot is going to be the numerator closure of some rational tangle. So how does the colorability of that tangle relate to the colorability of the knots that we can make out of that tangle? So there's quite a lot here, and our first step is going to be to figure out what does it mean to K-color a knot, and how does that relate to some questions about algebra and algebraic structure.